I'm just waiting for the guys to turn up. I mean, if you haven't seen the link, just make sure you see it. Like when you go home today, you can check the website to see that what we covered yesterday is there. Okay. All right, before I start, I just want to recap the stuff we did yesterday, right? So let me recap what we did yesterday. So basically we talked about the course, extreme values and financial risk. There are two parts to this course. The first part is extreme values, the second part is financial risk. But sometimes I will talk about extreme values only, sometimes I will talk about financial risk only. And I will jump between the two areas, right? Okay, so this is, can you see this from this side of the calculation? And then I talked about what are the reasons for this course. So these are two possible reasons why you want to take this course, right? And then I talked about some financial disasters. I went through I showed you some pictures of financial disasters. I don't want to show them again. And I also showed you some pictures of financial frauds, right? Because this course can be used to identify patterns that are not normal, right? When you identify patterns in stock market that are not normal, they may correspond to illegal activities, right? Such as financial frauds, right? Okay. Okay, so then I talked about what do you mean by extreme values? Extreme values, how do you define what an extreme value is? I talked about three definitions of extreme value. Yeah, the first definition is this one. So this is the first definition. Is it too bright or too dark? Can I switch off the slides or not? Is it okay? Is it okay like this? Right. Okay. So this is definition one of extreme value, where you take the largest observation as the extreme value. So in this case, this is the extreme value. Okay. And definition two of extreme value is this one, right? Where you draw a threshold that you think is high enough, and any data that exceeds that threshold is an extreme value. So this is definition two, right? And definition three of extreme value is just an extension of definition one. Instead of looking at the largest data point, you look at the first few largest. So in this case, the first 5 largest data points, right? This is definition 3. All right, then I started looking at definition 1. So this is where your mathematics comes in, right? In definition 1, the distribution function, or the CDF of Mn is the extreme value, is equal to this, right? So this is this distribution function of the extreme value under definition 1, right? Okay, and because we are trying to see how the extreme value behaves as n approaches infinity. Remember, n is the sample size. Because normally you are interested in how the extreme value behaves over very long periods of time, or very large sample sizes, right? And so for that reason, I took the limit, a limit of the distribution function as n approaches infinity. And it turns out the limit is either 0 or 1, which is not useful, right? So this is where this is where I drew parallel to the central limit theorem. Look, this is where the parallel between the central limit theorem and the strong law of large numbers comes. The strong law of large numbers, which is this one, is not very useful because the limit that you get here is a fixed number. Whereas the central limit theorem, which is a scaled version of the strong law of large numbers, is useful because the limit is the standard normal distribution, which is, as you know, all of you, central limit theorem is used in every branch of science, engineering, and medicine. Right? It is one of the most popular results in statistics. So for that reason, I wanted to apply a similar scaling. So instead of looking at the distribution of Mn, I look at a scaled version of Mn. So I subtract a constant Bn and divide by another constant An. And it turns out that the limit of this is the same as the limit of this, which I call star. Right? So the question is, what is star? Right? What is the limit in star? And the answer to this question is given by the extremal types theorem. So this is known as the extremal types theorem, or the ETT, which says the following. That is, if the limit exists, if the limit actually exists, then it must be of the same type as one of the three limits here: the Gumbel type, the Frechet type, or the Weibull type. All right. Okay, and then this is the main result in univariate extreme value theory. And then I explain what you mean by type. What does it mean to say that two distribution functions have the same type if this equation is true, right? And then, all right, then I talked about the case where, how do you know which of the three limits is attained? Given a distribution function of the data, how do you know which of the three types is attained? And to check that, you need to just check these three conditions, right? If this condition holds, then the limit will be Gumbel. If this condition holds, the limit will be Frechet. And if this condition holds, the limit will be Weibull, right? And only one of these three conditions will ever hold. That is, for example, if the first condition holds, then the second and third will not hold, and similarly. All right. So only one of the three conditions will ever be satisfied, if any. Right. Okay. Then I did some examples on the definition of W of f. W of f is the upper end point, which can be obtained by solving this equation fx equal to 1. Right? These are some examples. I also did one example. This is the last page I did yesterday. In this, I showed you that given an f, here in this case f is the exponential distribution function, what is the domain it belongs to? Is it Gumbel, Frechet, or Weibull? So here I showed you that the limit of this guy here is equal to, after some algebra, the limit you get is e of minus x, and hence condition 1 is satisfied. Hence the f belongs to the Gumbel max domain. In other words, there exist constants an and bn, an positive, bn any real number, such that the limit of this as n approaches infinity is this one. This is the Gumbel limit, right? So this is stuff we did yesterday. Any questions on this, guys? No? Yes, feel free to ask, guys. Are you clear about? This is everything that we covered yesterday. How are you, sir? You all right?
Yeah, good.
Cool, man. How are you? Any other guys? You have questions? Come on, guys. Talk to me. Sorry, I didn't bring any chocolates today. Maybe next week I will bring. Today I forgot. It's too busy today. Hmm? No. All right. So this is stuff we did yesterday. Now today what I'm gonna do is I'm gonna do more examples and stuff like that. So this is I just did one example yesterday. So I'm gonna do more examples today. All right. So this is example. Right? Oh, shit. No. Okay. Now, the first thing you need to work out is W of f. So you set fx equal to 1, okay, which implies that Alright, W of f is plus infinity, right? So let's check condition 1. Condition 1. Condition 1 says that according to condition 1, the limit of this must be EF minus x. Right? So let's see what it is. Right? Right? And the question is, can this be equal to EF minus x? I mean, can you find the gamma of t? Gamma t is a function of t, which must be a positive function, such that this is equal to this. Yes or no? No, right? You can't. I mean, there's no chance that the limit of this can be equal to this. All right. So the answer is that this cannot be equal to that. So hence, right, condition 1 fails to hold. Okay? And you see this, guys. Let me see. Alright, so condition 1 fails to hold. Alright, now let's check condition 2. Condition 2 says the limit right? This is condition 2, right? So we're going to take the limit Okay, so the 1 and the 1 cancels, so this will become right. Alright, so hence, so what you see that the limit becomes equal to 1 over x. So hence condition 2 holds with alpha equal to 1. Because if you look at condition 2 from yesterday, let me show you. Let me show you where it is. We did condition 2. This is condition 2. I don't know if we can see this. Here, over here. This is condition 2, where the limit must be x to the power minus alpha. So in this case, your alpha is 1, right? Okay, so it holds with alpha equal to 1. So in other words, right? So just give me a sec. It approaches this distribution. Alright, so the conclusion is that by the extremal type theorem, there exist constants a n and bn such that the limit of this as n approaches infinity. So the limit of this as n approaches infinity is this one. This is the Frechet limit. You should remember, with alpha equal to 1. Okay. All right. Any questions so far? Let me know, please. All right. The next one. So this is example 2. Example 3. Okay, suppose fx equal to x, which is the CDF of the uniform. I'm sure all of you know that uniform distribution on the interval from 0 to 1, right? It has CDF f of x equals to x, right? And I want to know which of the 3 domains this CDF belongs to. Is it the Gumbel domain, or the Frechet domain, or the Weibel domain, right? Alright, so before we do that, let's try to find W of f. So you put fx equal to 1, which implies that x equal to 1. So W of f is equal to 1. Right? Okay? It's easy, right? Finding W of f is easy because all you have to do is set fx equal to 1. Right? Now let's check condition 1. Condition 1 says you take the limit as t approaches 1, because your W of f is 1, of 1 minus okay. Alright, so this will be the limit as t approaches 1 of 1 minus okay. And this will be the limit of 1 okay. Right, the question is, can this now for condition 1 to be true, this limit must be equal to e of minus x. Can it be equal to e of minus x? Yes? No, right? Okay, so this, the limit of this cannot be equal to e of minus x. So this implies that condition 1 fails to hold, right? Okay, now let's look at condition 2 now. Now condition 2, can it be true? If you look at condition 2, guys, let me go back to what we did yesterday. This is condition 2. Can this be true? Because for condition 2 to true, W of f must be infinity. So because W of f is equal to 1, which is strictly less than infinity, this implies that condition 2 also fails to hold, right? Okay, guys. So the only condition that can be satisfied is condition 3. So that's what I'm going to check now. So I'm going to check if condition 3 is going to hold or not. So let me put this here. So I'm going to put this here. Okay, so I'm going to check. So the condition 3 is the limit as t approaches 0 of 1 minus f. W of f is 1. Sorry guys, can you see this? Yeah, okay. Okay, this is the condition 3. We need to show that, you guys okay? Alright, huh? T equals to 0. 0, because if you look at the stuff I gave you yesterday, this is the This is the condition that I gave you yesterday. T goes to 0 of this, and your W of f is 1 in this case. Yeah, okay, yeah. So, alright, so the limit is equal to x. So this implies that condition 3 holds with alpha equal to 1. Remember, once again, you should look at condition 3, which I talked about yesterday. The limit must be x raised to the power alpha. So in this case, your alpha is 1, right? So condition 3 holds with alpha equal to 1, okay? Alright, you see this is the limit when alpha equal to 1, this guy here becomes x to the power alpha, sorry, e to the power x, because the minus and the minus cancel out, so you get e to the power x when x is less than 0, and 1 if x is greater than or equal to 0. Alright, is that clear, guys, or no? Yes or no? Hello, guys. So this is the Weibull limit when alpha is equal to 1. Yeah. Okay. Yeah. All right. I would like to do one more example. Example 3. So this is example 3. Let me do example 4. This is a little bit tricky. Example 4 will be, suppose, oh shit, not this one. No. If you have questions, guys, let me know. Example 4, okay? Suppose f of x is equal to alright. Okay, this distribution is known as the exponentiated exponential distribution, right, where the CDF is 1 minus e of minus x, everything raised to the power a. A is the positive number, and x is also positive, right? So the first thing we need to do the first thing we need to do is what? We need to find w of f. So you need to set f of x equal to 1, which implies that 1 minus is equal to 1, which implies that 1 minus e of minus x is equal to 1, which implies that e of minus x is equal to 0, which implies that minus x is equal to minus infinity, and this implies that x is equal to plus infinity. So hence w of f is equal to plus infinity. Okay. All right. So okay, now we need to check condition 1, then and so on, right? So let's start with condition 1. Okay, which is okay. All right, now I'm sure all of you guys are experts in calculus. I mean, you must have done calculus a long time ago, right? Can you tell me how to find the limit of that as t goes to infinity? Hmm? Any ideas? All right, let me give you a hint, right? As t goes to infinity, what does this go to? It goes to 0. And so is this one. This also goes to 0. Right? Now, there is a result, I'm not sure whether you know. If you have something like 1 minus z, if you have something like this, then this behaves like do you guys know this result? This is known as, it's basically a version of the binomial theorem. I mean, I think you must have seen this before in your calculus courses. If you have something like 1 minus z power a, and z approaches 0, then this is approximately equal to 1 minus a times z. You seen that or not? Yeah. Yes, good. All right, so I'm gonna use this result, right? So using this result, guys, you can write, because these two guys approach 0, right? You can say that this is equal to the limit, right, of using this identity. You can say this is Yes, you see what I've done? I have used this result here to get from this line to this line. Okay. Now these ones will cancel. Okay, and the an and the an will also cancel. So you will get the following. You will get this as the limit okay, and this is equal to the limit okay, and this is equal to e of minus x if right, hence right, that is there exists an and bn such that the limit of f an x alright. Okay guys, so the limit that we got is e of minus x, so hence condition 1 is true, alright, and hence the limit it will be Gumbel, alright, as I just written, right? Okay, alright guys, so that's 4 examples, that's enough for the moment. So the next thing I want to talk about is the following. I'm trying to remember what it is, I just forget. Sometimes I leave my papers. Just a minute, give me a sec, guys. Oh. By the way, you should go to quiz 1. This is quiz 1. You should now be able to do quiz 1, given the material that we have covered. You should be able to do quiz 1 now. So if you already done it, you can hand it to me whenever. I mean, you don't need to wait till the deadline, which is the 8th of December, 8th of October. I mean, 8th of October. If you've already done it, you can hand it to me. Whenever you're done, you can hand it to me. Okay, and this is worth 2 marks. Right? Each quiz is worth 2 marks. Right? There will be 5 in total. Right? Okay. All right. Next thing I want to talk about is the following: is you should go back to the stuff I gave you yesterday. I'm still trying to. Oh, here it is. All right. You should go back to the stuff I gave you yesterday. There are conditions. The conditions I gave you yesterday are these ones. All right, these are the conditions I gave you yesterday. Remember this, right? These are the 3 conditions I gave you. So the first condition is for the Gumbel type. This is for the pressure type. and this is for the viable type. Now each of these conditions mainly involve F, capital F. Remember, capital F is the CDF of the data, right? Okay. Now there are conditions different from the. I'm going to give you some conditions which are different. So the title is the following. Okay, alternative conditions for checking next domain. So these are one set of conditions. I'm going to give you some alternative conditions now, right? Now I need to, before I give the conditions, I need to define a few things. Right, so let little f denotes the derivative of the capital F. So in other words, it's the density function, right? And let A of t and let B of t okay. Alright, so I define these three functions. So the first function is the density function. So it's the derivative of the CDF is the density. The second function is called A of t, which is the inverse function of f worked out at 1 minus 1 over t. The third function is this, right? Okay. Under these conditions, under these definitions, the conditions are as follows. For type 1, that is for the Gumbel type, right, this condition must be true. So if this is true, then f belongs to a Gumbel type. Okay. For type 2, which is the Frechet type, right, and for type 3, which is the Weibel type, So these are the three conditions for the three different types. So these three conditions are equivalent to the conditions I gave you yesterday. So for example, this condition here is equivalent to this condition, and this condition is equivalent to this one, and this condition here is equivalent to this one. All right. So because sometimes, like in the exam or like in the quizzes that I've given you, sometimes it's easier to use this one than the conditions I've given you there, right? Okay, so that's why I'm giving you these alternative conditions, right? Okay. All right, now when you put it here. Now let me try to redo the 4 examples I've done using the alternative conditions. So let's start with example 1. So example 1, which I did yesterday. This is example 1. Now for this f of x, you may remember it is this one, right? Okay, so the first thing we need to work out, guys, is we need to find the little f of x, which is the derivative of the capital F of x. What is that? What's the derivative of this? E of minus x. Okay, and the second thing we need to work out is the a of t, which is the inverse function of f. So to find the inverse function, guys, all you have to do is just set fx equal to, say, in this case you want to find the inverse function at 1 minus 1 over t, right? So you set this equal to 1 minus 1 over t, and then you solve for x in terms of t, so which implies that this, and this implies minus x equal to minus log of t. So x is equal to log of t. Alright, so in other words, your AT is equal to log of t. Do you see what I've done? Because you see, according to this condition, we need to work out a of t, which is defined as the inverse function of f at 1 minus 1 over t. So to work out a of t, what I have done is to set the CDF equal to 1 minus 1 over t, and then solve for x in terms of t. So we get x equal to log of t. So a of t equal to log of t. Is that right? You know how to work out. I'm sure you must have done this ages ago, how to derive inverse functions, right? Alright, then b of t, according to this, b of t is t times f of at. F we know is e of minus x at, right? So this will be t times e of minus log of t. Now what is, so this is t times 1 over t, which is equal to 1, right? So b of t is equal to 1, right? Okay, so now this implies that if you are going to check condition 1, you're going to look at the limit of btx divided by bt as t goes to infinity. which is the limit of 1 divided by 1 as t goes to infinity, which is 1. Right, hence right. Okay. Do you see what we've done or not? I mean, you guys play about this? What about you guys? Okay. So this is another way of checking the one of the three conditions, right? What time is it now? We have time. How much time we have?
10 to.
10 to? Oh, it's 5 still. Come on. When I'm with you guys, the time flies. I can't say. Alright, guys. I'll see you Wednesday, next on Monday. But if you have any questions before that, you know where to see me. And those, you can. I'm in my office 11 to 5 every day, Monday to Friday. And you can also arrange to see me during weekends because I live very close to ATD. Okay, guys. So have a good week and have a good weekend. Right? I'll bring you more chocolates on Monday. And try to bring more students to this class. Yeah?
Yeah, but they said like they'll do it in the chair after they said
Oh, okay. Alright, man. See you. Have a good day. Have a good evening. Hello, how are you?
Can I see one of your notes because it's been passed away? So example 4. Yeah. Can I see that because?
Oh, okay.
Yeah.
Example 4. Let's
Yeah,
see.
for the last one is the tricky one. Yeah. So I need to I need to write down what affects it. 1 plus E minus it's A, right? Yeah.
Yeah.
That's okay. And also for these kind of things, is that got any tricky things to remember when 1 plus that to the power of A maybe?
I will give you this before the exam. I'll give you a formula sheet to remember.
Yeah, I've already saw on your website to remember.
Yeah, I think this may be, I don't know whether it's there or not. Maybe, is it there in the formula sheet?
No, it's not in there.
Maybe
this one's not in there.
Okay, maybe in that case you don't need to remember this.
Okay, I see.
Yeah.
Yeah. Okay.
Only those in the sheet you need to remember. Only the formulas in the sheet.
Yeah, it's okay. I mean, during we do the problem sheet, I know there's another is e to the power of y when y goes to what and this goes to 1 minus or 1 plus y.
1 plus y.
1 plus y, right?
Yeah.
Is that got this? So beside of these two, is there any others we need to remember when we do the problem sheet?
Well, yeah. Only those two.
Those two, right?
Yeah, only
There's
those
no
two.
more.
Yeah.
Okay.
Yeah.